Welcome, welcome, welcome. We're trickling in. All right. So Thursday we looked at all of Chan's practice exam. And then thing here. 1 second here. We got a little bit off. And then we started looking at some of the first one from No. So unless there's specific things you want to look at, I'm happy to start where we left off. But so for anyone that has an exam tomorrow, are there specific things you would like to see? It's okay if you don't have anything to say. I'm just asking because it's good to ask. It's very in the way. Maybe a little out of focus. So here's where we left off in the first practice exam from now. With some true false statements, which always feel like, I don't know, they always feel harder than they should be, maybe. I should really double check to be sure we're on the right side. There's so many pages. Thanks. Oh no, so actually, sorry, before this page, we were actually right here on page 607, which was computing this gnarly looking derivative. The derivative of e to the cosine of x squared plus tangent of x squared. That is written in maybe the worst way possible. So I have a question actually for you all. If we write it as cosine of x squared, do you think that means we're squaring the x or the function? I think the function too. Although really, if you wanted to properly indicate that, you should really either write it as the abbreviated notation cosine squared of x, or if you're going to put parentheses around it, you should really put parentheses around the whole thing. So I think that's what's meant. That's what I would assume is meant. Honestly, if I was not sure, I might ask during the exam. Like if the notation seems unclear, I don't think it's improper to clarify. I could be mistaken. Your teacher might feel differently, but what's the worst that happens? They say I can't tell you anything, and you have more the same amount of information you have before. So it's okay to ask questions during a test. You might just not get an answer. So for the derivative of e to the row stuff there, we know that our derivative is going to be e to that same stuff times the derivative of that stuff, which you should write the derivative there. In this case, that's going to be e to the, I would write it as cosine squared of x plus tangent squared of x times, I probably wouldn't usually write this step, cosine squared of x plus tangent squared of x prime. And then we're going to rewrite it as e to the cosine squared of x plus tangent squared of x. And then we're going to take the derivative, remembering that we really mean cosine of x quantity squared. So we take the derivative of something squared, we get 2 times that something to the first power times the derivative of that something. So the derivative of cosine squared is going to be 2 times cosine of x to the first power times the derivative of cosine, which is negative sine of x. Similar deal for tangent squared. The derivative of tangent of x to the second power is going to be 2 times tangent of x to the first times the derivative of tangent, which is secant squared. And that's as far as we should go. Now let's look at the true false stuff. As usual, please feel free to ask questions if you have them. So for each of the sentences below, circle whether they're true or false. I will also point out this question. So unlike some true falses, this doesn't say anything about justifying, showing a counterexample, anything. It just says pick an answer, right? We don't need to offer any justification unless asked to. So let f be differentiable, then f is continuous. Or in other words, if the function is differentiable, then the function is continuous. That is certainly true. Differentiability implies continuity. The other direction is not. So if the statement said, let f be continuous, then f is differentiable, that statement would be false, or really not always true. There are certainly lots of continuous functions that are also always differentiable, but there are some that aren't. The best example is probably the absolute value function. That's a good example of a function that is not differentiable everywhere, but is continuous everywhere. Another good example is x to the 2/3 power. Let's look at the second one. Let f and g be differentiable functions, then the derivative of f of g of x is f prime of g prime of x. True or false? Is that like the derivative of f of g of x? Definitely false, right? The derivative of f of g of x, we should be using the chain rule, which would be f prime of g times g prime. We know it's false. We've already used the chain rule a few times. I would write here the derivative of f of g of x is f prime of leave the insides alone, then multiply by the derivative of the insides. Again, not necessary. I just feel like writing. The function y equal to cosine of 5x satisfies y double prime equals -5, times y. So you could certainly get away with circling one of the answers here, but this is a case where I'd probably show some work because I need to do the work to make sure it's right. So I'm trying to show, does the second derivative of cosine of 5x equal -5 times cosine of 5x? The answer is going to be false. I think they meant it for I kind of think they meant for it to be true, but they missed something. So the first derivative, y prime is negative sine of 5x times 5. The second derivative is going to be negative cosine of 5x times 5 times another 5. So y double prime looks like it's negative y times 25. Almost true, is still false. I will point out that if this had been a -25 instead of a -5, then it would have been true. So just for example, if your function had been y equal to sine of 3x, and we said it satisfied y double prime equal to -9 times y, you should show on your own that this is true. We take the derivative twice, you'll get -9 times the original function. Cool. This next question is interesting, or this next, I should say, statement. The ellipse, and that is an ellipse, x squared over 3 plus y squared over 4 equal to 1, can be realized as a graph over x. I have no idea what that means. Really, I'm not kidding, not like me pretending like I don't know so we can figure it out. I don't know what your instructor means with that statement. My best guess is that he means that we can think of it as a function of x. And that is false, right? An ellipse, famously, like a circle, fails what test to be a function? The vertical line test. So if this means what I think it means, then it's false. We can't, quote unquote, realize this as a graph over x. But I guess I should ask, did he post solutions to this? I think he did, right? Think so? I think I posted them in Canvas. I guess we should check. Yeah, well, we'll come back to that. So let's look at this last one here. let ax plus by equal to 0 be a line with b and a not equal to 0. Okay. Then the slope of the line perpendicular to ax plus by equal to 0 is negative b over a. Good question. Here's what I would do. I would first write it in a way that looked more familiar to me. So I'm going to take this ax plus by equal to 0 and solve for y. So I know it looks like the usual equation of the line. So by equals negative a times x. Y is equal to negative a over b times x. That's the slope of this line. The slope of the perpendicular line would be positive, or I should say the opposite sign, reciprocal. So it should be positive b over a. So again, false. Right? He said the perpendicular slope should be negative b over a. We got positive b over a. Interesting. Oh, sorry. Yeah, apologies. All right. I feel compelled to go look at the canvas. Only take forever. The login. Let's go and see if I actually did post the solutions like I said I was going to. Yep, I did. So I think this was the first one. Let's take a look. Let's see, was it the first one? Yep, that's the one we did. So we scroll down. That doesn't. Oh, that does the solution. Okay, cool. So you really type out the solutions there. Okay. Sure. We did all that. There's your derivative of that. So I will point out that this function here, we do have that, right? It's cosine of x quantity squared and tangent of x quantity squared. We can tell by looking at the derivative, right? Our derivative is 2 times cosine to the first times the derivative of cosine, which is negative sine, and 2 times tangent to the first times the derivative of tangent, which is secant squared. So that tracks. And then true or false. So, right, true, false, it's not the chain rule. False, negative 25. Yes, okay, so that is what he meant by that. That when he writes that you can be realized as a graph over x, what he means is it's a function of x, is what he means with those words. Okay. And then also false, the last one. Okay, great. So I guess we could look at the other one. If I printed it out, did I print it out? I sure did. Seems like a decent use of our time. Maybe, probably, yeah, I think so. Guys, like, do whatever you do. All right, so I imagine this one's similar-ish as far as the content, but let's take a look. So, solve the following problems. Differentiate this twice. Whenever you're taking a second derivative, after you take the first derivative, I really can't recommend enough simplifying as much as possible. So if we write this as f of x equal to e to the x plus 1 to the 1/2 power, I would first just differentiate it as usual. So it's going to be 1/2 times e to the x plus 1 to the negative 1/2 times the derivative of the inside, which is e to the x. That's kind of it. And then for the next derivative, you could simplify this, I guess. I mean, the only real simplification you could do if you wanted to is you could write it as e to the x over 2 times e to the x plus 1 to the positive 1/2. I don't know if that's better or not. I don't really have an opinion one way or the other. I would probably leave it like this and just use the product rule to take the next derivative. So for the second derivative, that 1/2 constant is going to hang out in front. And for the derivative of e to the x plus 1 to the negative 1/2 times e to the x, we're going to use the product rule. So the derivative of the first part is going to be negative 1/2 e to the x plus 1 to the negative 3 halves times the derivative of the inside, which is e to the x, times the other piece, which is e to the x. If it helps, and it might, you might actually like call these things different names. Like you might call this g and this h. So that when you take the derivative, you're like, okay, there's my g prime. And then that e to the x isn't playing the role of this e to the x. We still have to multiply by h, so we don't forget that. And then switch it up. The other piece is going to be our g piece left alone, e to the x plus 1 to the negative 1/2, multiplied by the derivative of e to the x, which is just e to the x. There's our g times h prime. And I wouldn't do anything else, right? I would leave it like that. There's no point in simplifying unless we've been asked to. Oof. Ugh. This next one looks interesting. So we're asked to differentiate x to the sine of x over x squared plus 1. I'm pretty sure we have to use logarithmic differentiation here. It'd be more typical if it was just x to the sine of x, but since we have all of that, it's still something we can use logarithmic differentiation for. So we're going to start by writing it as y equal to x to the sine of x over x squared plus 1. So I'll remind you that, yeah. No, that's what you should do. You could also approach this by writing it as e to the natural log of that whole function. I don't think that's the better way to do it. I think this is the better way to do it. If you recognize you need to use logarithmic differentiation, it is better. I want to say you have to. You don't have to technically. But the nicer way of doing this, easier in my opinion, is to write y equals the thing you're trying to differentiate, then take the natural log of both sides, then simplify the right-hand side. So we're going to have the natural log of y equal to the natural log of all this stuff. And then we're going to break it apart. We're going to write it as the natural log of the top part, natural log of x to the sine x, minus the natural log of the bottom part. And then we're going to bring the sign down in front. So we're going to rewrite it as the natural log of y equal to sine of x times the natural log of x minus the natural log of x squared plus 1. I like this one better than the previous one we had that had like 4 pieces and you had to like break it up. Like that one feels like you could have kind of brute forced it and just done the product rule and the chain rule a few times and made it work. This one, you really are kind of forced to use logarithmic differentiation. Next, we would differentiate both sides. So we're going to get 1 over y times y prime on the left. On the right-hand side, a few things going on. For the sine times natural log, we have to use the product rule. So it's going to be cosine times leave natural log of x alone, plus sine times the derivative of the natural log of x, which is 1 over x, minus the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. There isn't really much simplification to do. The only thing I can really do is write this as sine x over x, and this is 2x over x squared plus 1. I think you should not write this step. I think you should skip this step where I just write y times all this stuff. And instead, make the mental step of just replacing y with what y is equal to, which is x to the sine x over x squared plus 1. So you should skip this and just write it as y prime equal to x to the sine x over x squared plus 1 times everything in our brackets there. Cosine of x times natural log of x plus sine of x over x minus 2x over x squared plus 1. This seems like one worth practicing. No, I mean, they're all seem like they're worth practicing, but I think you also try one right now. So here's what I want you all to try. I want you to try to differentiate y equal to x to the 4th minus 2 over x to the 2 cosine of x. Give that a shot. I'll give you like 3 minutes. 3 minutes seems like a long time. I'll give you 2 minutes. All right, it's been a little more than 2 minutes. So the process is the same every time. How do I know I need to use logarithmic differentiation? Either it's a gross fraction with a lot of products, or in this case, you have something with x to a power of something with x, right? That's the key indicator that we should be using logarithmic differentiation. So same process, take the natural log of both sides. Break it up. Now I'll point out that power can't come down in front until it's its own piece. So we have to break this up as the natural log of x to the fourth minus 2 minus the natural log of x to the 2 cosine of x. And then we can simplify that further as we can't do anything with this. Natural log of x to the fourth minus 2, it's stuck as it is. You can't bring that 4 down because you have that minus 2 there. It just is. So this is natural log, excuse me, of x to the fourth minus 2 minus the natural log. Oops, I should have brought the 2 cosine x in front. Sorry. Minus 2 times cosine of x times the natural log of x. And now we're in the same boat we were before. We're going to differentiate both sides. Right? It's still natural log of y on the left. We get 1 over y times y prime. That's always what you get when you differentiate natural log of y and you're assuming y is a function of x. On the right-hand side, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Over here, we have a product rule. So the derivative of 2 cosine is negative 2 sine multiplied by natural log of x plus 2 cosine left alone multiplied by 1 over x. Okay, I'm actually going to skip the step this time and not just say I'm going to skip it. So when I write y prime, it's going to equal y, which is this. It's going to be x to the fourth minus 2 over x to the 2 cosine of x times all of that. And you don't really need to simplify it, but it just feels like it's easier to write it down if I do a little simplification. So I'm going to write this as 4x cubed over x to the fourth minus 2. Minus a minus is plus 2 sine of x times natural log of x. And minus that is minus 2 cosine of x divided by x. it seems pretty likely you'll see some logarithmic differentiation on those exam. Because I'm looking at the other problems, and there's like two more logarithmic differentiation problems. So seems like it's gonna come up. All right, let's look at page three, right? Page three. Yeah, page three. Solve the following problems. Use implicit differentiation to find the tangent lines of the cusp x cubed equals y squared and the parabola y squared equals x. So when you see a question like this and they didn't specify a point, you have to make up your own point. And I think he likes to call it x naught, y naught typically. You can call it something else, but x naught, y naught is probably the way to go. So we're going to find the equation of the line tangent to, we'll do this one first, x cubed equal to y squared at the point x naught comma y naught. So let's take a look and see. So we're going to find the slope of the tangent line by first taking the derivative of both sides. So we've got 3x squared equal to 2y times y prime. Solving for y prime, we get y prime equal to 3x squared over 2y. And then if we plug in our point to find our slope of the tangent is going to equal y prime evaluated at this made up point, x naught comma y naught, which is going to be 3x naught squared over 2y naught. And then to find the equation of your tangent or of any line is just y minus the y coordinate equals your slope times x minus the x coordinate. So the equation of my tangent line is going to be y minus y naught equal to my slope, 3x naught squared divided by 2y naught times x minus x naught. Which feels super funky. In fact, it makes me want to look at the solutions to make sure he's not doing something else. We're probably right, but it's good to check. Let's go back here and look at the modules. It feels moderately disappointing that we're not just given a point there instead, but oh well. Let's see. So, yep, takes the derivative of both sides, solves for the derivative. He gets 3x squared over 2y. Oh, at the point 0, 0 and y equals 0, the slope becomes undefined. So the vertical tangent line is the tangent line. Okay. Okay. So interesting. All right. We have to be even more explicit. So we were not careful enough here. So the fact that he pointed out that it is a cusp means there is a place where the derivative is undefined, right? Cusps are like pointy points where the derivative is undefined. So as long as the derivative is defined, we're good to go. But if you look at your slope of your tangent line, you can see that this slope is going to be undefined if y is equal to 0 or y naught is equal to 0. So if y naught is equal to 0, then y prime is undefined. If your derivative is undefined, what kind of line do we have? Or what kind of tangent line do we have? A vertical one, right? Vertical lines are the only lines that have undefined slopes. So y prime is undefined, meaning the line is vertical, meaning the equation is x equal to something. But we have to figure out what x is equal to. So we have to go back and say, okay, well, if y is 0, then x also has to be 0. So if y naught is 0, then we also have to have that x naught is equal to 0. And that means our equation, our tangent line, is the line x equal to 0. Okay. Mildly annoying. And I think a similar thing is going to happen for the other equation. In fact, the other one's actually easier to draw though. So this one, x cubed equal to y squared, like it's kind of weird to think about drawing, although it's not impossible. On the other hand, x equal to y squared is something we can all draw. it is a parabola. Which way does it open? To the right. So if we draw this parabola, not that you have to draw it, but it's not a crime to draw it. And it helps me to be like, okay, well, it seems pretty clear that I'm going to get a vertical tangent line again at the origin. So I'm pretty sure at the origin, I'm going to get x equal to 0 again as my tangent line. But again, doing it the way the instructions have told us to do it, which we should follow the instruction, we're going to find the derivative. So differentiating y squared equal to x, we're going to get 2y times y prime equal to 1. So that means we're going to get our derivative is equal to 1 over 2y. So let's do it more the way he did it. So we'll start off by saying if y is equal to 0, then y prime is undefined. So our tangent line is vertical. And it's going to be, well, if y is 0, x is 0, and it is x equal to 0. On the other hand, if y isn't 0, then our slope is going to be 1 over 2 y naught, plugging in y naught for our y coordinate there. And our equation is going to be y minus y naught equal to our slope times x minus x naught. I don't know if I could think of a more annoying way to ask this question, so I'm sorry. But that's what but you know what you're up against, right? You know you're going to see something like, it's like almost a guarantee you're going to see a question like this on your exam, where he's asking you to find the equation of the tangent line using implicit differentiation, and he's not going to give you a point. So you know that when you see this, you just get to call the point x naught y naught and write the equation very generically. And then just be careful, be on the lookout for if you have something that he describes as having a cusp, right? You know it's going to have a vertical. There's going to be some place where the derivative is undefined. So when you do these problems, make sure you look out for a place where the derivative is undefined. Both of these, it was undefined when y was equal to 0. So be careful. You can think of Eric. Yes, sorry, yeah. And actually, I imagine he did the same thing for his solutions, but let me just double check so I'm not missing anything silly. Yep, same thing. Yes. Yep, exactly what we just did. Cool. All right, let's see what's on the other side of this page here. Oh yeah. Consider the curve x cubed plus y squared equal to 1. Feels implicit to me already without reading anything else, but right, you don't have y explicitly written as a function of x, so I'm thinking implicit, although I'm not going to start doing that until I read the rest of the question. Compute the tangent lines and the normal lines of this equation. Find the points where the derivative is not defined. I think we just did that question. Feels like a lot of repetition in this practice exam, I gotta say. So, yeah. Show that there are points where dx dy is equal to 0. Okay. All right. So, fun times. So let's compute the tangent lines and the normal lines. We're going to start by finding the derivative. And I'm going to use the Leibniz, the dy dx notation here, just to make sure we're kind of all on the same page. So taking the derivative with respect to x, we're going to get 3x squared plus 2y times dy dx equal to 0. Solving for dy dx, because we're going to try and find the equations of tangent lines. So dy dx is going to equal negative 3x squared divided by 2y. Let's just focus on the tangent lines right now. So for the tangent lines, and let's see, okay. Gosh, there's so many, this question has like so many parts. Find the points where dy dx, be careful here, because if you don't read carefully, that's dy dx, that's dx dy. So you have to make sure you're looking carefully at what's written. It'd be really easy to miss that. So find where dy dx is not defined. Well, this is not defined when y is equal to 0. So dy dx is undefined at the point where y is 0. I'm going to find the x coordinate as well. I think you should too. So in my equation, x cubed plus y squared equal to 1. If y is 0, what does x have to be? Got to be 1. So it's undefined at the point 1 comma 0. Okay, we answered that question. Sure, let's go ahead and find the equations of the tangent lines. So, yeah. I wonder, I'm curious. I'm just going to go with my usual thing. So finding the equation of the tangent line at the point x naught comma y naught, we get the usual tangent line equation is going to be y minus y naught equal to your slope, which is going to be your derivative with your x naught y naught plugged in, negative 3 x naught squared over 2 y naught times x minus x naught. Unless, of course, y is equal to what? Right, and if y is 0, then our tangent line has an undefined slope, so it's a vertical line. Y equals 0. Our tangent line is, of course, going to be what? Or I should say x equal to what? X equal to 1, right? Because that's the x value when y is 0. Interesting. All right. And then we're going to find the normal lines as well. The normal line, actually, I will say the way he's written this problem does make it really easy to find the equation of the normal line. The normal line, you're just going to take the opposite inverse of the slope and leave everything else the same. So the normal line, you're going to have y minus y naught equal to positive 2y naught over 3x naught squared times x minus x naught. Unless, of course, x is equal to 0. And if x is equal to 0, then, oh my God, then the normal line would be vertical. Yeah. So if x was equal to 0, looking back at our equation, y could be plus or minus 1. So unless x equals 0, we get normal lines that are, oh my God, brain. No, it should still be a vertical line, right? It should be get x equals 0. I think. Right? We're saying this is the equation of the normal line. So the tangent line would have a slope of 0, and the normal line would have a slope of undefined. Right. I'm convincing myself more than I think I'm convincing you all. Anything else to say about that? We do have to also show that there are points where dx dy is equal to 0. I'm pretty sure that's where the derivative is undefined. So I'm fairly confident that this is that point. It's kind of interesting. It's kind of weird. I'm going to show the long work, but I'll point out that kind of annoyingly almost, but actually also really nicely, if you find dx dy, it literally is the reciprocal of dy dx. Like it feels like it shouldn't work that way because you're talking about a derivative, but it does actually work out that way. But let me show you the long way just to kind of point out that it does work. I'm going to use the space over here. So we find dx dy, pretending like y is the independent variable and x is the function. Then if we differentiate this, we're going to get 3x squared times dx dy plus 2y equal to 0. And then if we solve for dx dy, we get dx dy equal to negative 2y divided by 3x squared. Well, that looks familiar. It looks like the reciprocal of that. Or the reciprocal of that. So it's not just like for fun, it actually works. And then if y equals 0, dx dy is equal to 0 as requested. So this point here where dy dx is undefined is also the point where dx dy is equal to 0. That's kind of neat. It also makes total sense, right? If one slope is 0, the perpendicular slope should be undefined, and vice versa. And I'm curious what he has written about this because I am. Let's see. He finds the derivative in the way we did. He finds, yep. And then, oh, cool. So he did different work, which is totally fine. He found dx dy literally just by taking the reciprocal on both sides, which is totally valid. Right? He went from this step right here, dy dx equal to negative 3x squared over 2y, to this thing right here by literally taking the reciprocal of both sides. He just flipped both sides. Then you can find the normal and tangent lines. So, right, the tangent line has that slope. The normal line has that slope. Find where dy dx is on. I don't know why there's a 3. Oh, okay, there's just the numerical. So to find where it's undefined, he's just setting the denominator equal to 0. And you get x equal to 1. And then that's also where dx dy is equal to 0. Yeah, okay. I will point out, he didn't consider the tangent line equation being vertical. Poor form. But it's fine. I wouldn't worry too much about it. All right. More implicit differentiation. Good Lord. I think there might be some implicit differentiation on your exam tomorrow. Just to guess. Yeah. I think that's the focus for the day. Which I suppose if I'd been more proactive about it, I could have let you all know that that's what I was thinking about doing. But sorry, sometimes my brain just doesn't want to work all the way. So you're welcome to stay. You also don't have to if you feel like it's not adding a lot of value. Fair enough. I understand. So let's look at this next one. We're going to use implicit to find the derivative of negative y squared plus 3x equal to 0. Find its slope at the point 0, negative 1. Okay, this one I kind of like. Unless otherwise stated, we're always assuming that x is the independent and y is the function. So if we're going to differentiate both sides of negative y squared plus 3 to the x equal to 0, we're going to get negative 2y times dy dx plus the derivative of 3 to the x. I do think is a formula you should remember. When you have some non-e base to the x, you just get that base to the x times the natural log of that base. The derivative of 0, still 0. And although this one is not too complicated to solve for dy dx, if you can just plug in your point, you might as well just do that. So if you have a point to plug in, do that before you do any algebra. So plugging that in, we're going to get negative 2 times negative 1 times dy dx plus 3 to the 0 times natural log of 3 equal to 0. And then we're going to solve for dy dx. So 2 times dy dx is going to equal, let's see, 1 times natural log of 3. So it's going to be negative natural log of 3. And then divide both sides by 2 to get that your derivative, aka your slope of your tangent line, is negative 1/2 times natural log of 3. And then we're going to, oh, that's it. That's all they didn't find. So I was expecting them to ask to find the equation of the tangent line. This is a really good example of why it's good to read the question carefully, because I was about to do more work than I really needed to. There's your slope right there. All right, more logarithmic differentiation. So differentiate x to the e to the x. There are a few ways of doing this. In my opinion, it is best to write it as y equal to whatever your function is, and then take the natural log of both sides. And then we can bring the e to the x down. One thing worth noting is that when you have an expression like this and there aren't any parentheses, the assumption is that x to the e to the x is equal to x to the parentheses e to the x. It is not the same as x to the e to the x. I know that might seem like not an important distinction, but it really is. I'll say over here, 3 to the 3 to the 3. It's very different if you look at it as 3 to the 3 cubed versus 3 cubed to the third. Those are very, very different things. 3 to the 3 to the 3 is 3 to the 27th power, which is a lot of threes. 3 to the 3 to the 3 is 3 cubed times 3 cubed times 3 cubed, which is really just 3 to the 9th. So very different. It's important that we recognize that. So in this case, since there aren't parentheses, we assume it looks like that. So we're going to bring that e to the x down in front. So we're going to say natural log of y is equal to the e to the x times the natural log of x. Then we differentiate both sides. We get 1 over y times y prime equal to the derivative of the right-hand side is going to be the derivative of e to the x times natural log of x plus e to the x times the derivative of the natural log of x. Again, if you're doing it this way, which I do recommend, the next step we want to solve for y prime and replace y with what it's equal to. So our solution is going to be y prime equal to y, which is x to the e to the x, times all that. E to the x times natural log of x plus e to the x divided by x. That's the work I would choose to show. Next problem, very similar. And for this one, instead of doing it the way I like to do it, I'll do it the other way, which you could approach a problem like this. So the other option for differentiating something where you would use logarithmic differentiation like this is instead of writing it as y equal to something and then taking the natural log of both sides, you can say, well, I'm going to take the derivative of this function, x squared plus 1 to the sine of x, and then rewrite it as the derivative of e to the natural log of x squared plus 1 to the sine of x power. The point of that being that then the sine of x can come down in front of the natural log that's still in the exponent. So this sine here can come down in front of the natural log because of the rules of logarithms. So we can say, great, we're going to take the derivative of e to the sine of x times the natural log of x squared plus 1. Again, not the way I prefer to do it, but this way also works just fine. And if you want to do it this way, you totally can and should. I will point out, I don't think this method would have been great for the first one we did on this practice. Why did you go away? Sometimes this thing just wants to stay. I don't know what's wrong with this. Why would you do that to me? Thought we were friends. Okay, so what I was going to point out is the first problem we did like this, that was the, where'd you go? It was the x to the sine x over x squared plus 1 problem, that one. Technically, you could do this one that way as well. You could write it as e to the natural log of all of that. But then your exponent is going to be really super gross. It's going to be e to the natural log of x to the sine x minus the natural log of x squared plus 1, and then the sine x comes down. So we really don't want to write this as e to the natural log of x to the sine x minus natural log of x squared plus 1, and then rewrite it as e to the sine x natural log of x minus natural log of x squared plus 1. That's just terrible. I would not recommend doing it. Although you could do it that way. It would work. It wouldn't be a whole lot more awful than this. I just think it's harder to keep track of things that way. So doing this one that way, though, is not too terrible. We're going to differentiate. We've got the derivative of e to the stuff. The derivative is going to be e to the stuff times the derivative of the stuff, just like it always is. So it's going to be e to the sine of x times natural log of x squared plus 1 times the derivative of sine of x times natural log of x squared plus 1. And then we differentiate. Now, normally we just do the derivative time. I will say, when you do these problems, I think you should always rewrite this part as the original way it was written, which was x squared plus 1 to the sine of x power. So that when we rewrite this, we end up getting x squared plus 1 to the sine of x power times the derivative of this product, which is going to be cosine of x times the natural log of x squared plus 1 plus sine of x times 1 over x squared plus 1 times 2x. But I do think it's important to rewrite e to the sine times natural log of x squared plus 1 as x squared plus 1 to the sine of x. Just undoing the change we made in the first place. All right, and then on the last page, more true false. I'm curious. So for your first exam in nose class, was his actual exam similar as far as like the layout? Okay, then you what? Okay. Okay. So then I think that's a reasonable expectation for your exam tomorrow. So you should be expecting very similar content, same layout, same types of questions. I would hope it's more similar to your first one, just because I feel like your first exam had a little more variety to it. This one feels like it's a lot of implicit and a lot of logarithmic differentiation. So yeah, okay, well then you know what to focus on. All right, let's look at this last true false page. For each of the sentences below, circle whether they're true or false. So I should ask you, does he expect you to write anything else? Okay, good. So let f equals x sine of 1 over x where x not equals 0 and f equals. So I should point out one thing I'll say. You should not leave any of these unanswered. Whether or not you've actually looked at them, if you've got a minute left, great. Pick them randomly. But pick an answer, right? It's better to take a 50-50 shot than not write anything down at all. So definitely circle something on each of these, whether or not you've actually looked at them. All right, so let's take a look here. So f equals x. This one looks hard. Let's skip it and go to the next one. I'm running out of time. So let's look at the next one. The inverse of x cubed is differentiable x equal to 0. What's the inverse of x cubed? X to the 1/3. What's the derivative of x to the 1/3? 1/3 x to the, which is 1 over 3 times x to the 2/3. If you plug in 0, it's undefined. False. Not differentiable at 0. Here's another way of thinking about that. What's the derivative of x cubed? 3x squared. What do you get when you plug in 0? What's the inverse of 0? Wait. What's the inverse of 0? Let me say that before. What's the reciprocal of 0? Undefined, right? The reciprocal of 0 is 1 over 0, which is undefined. And there's a theorem about how the derivative of the inverse is the reciprocal of the derivative. So since the derivative, right, the derivative of x cubed is 3x squared, and if you plug in 0, you get 0. So then the derivative of the inverse is going to be 1 over 0, which is undefined. There's a couple ways you can think about it that way. Ugh. The function y equals, you know what, I this problem, but I shouldn't, because it's actually not that bad. This problem is really not terrible. We have to find a first and a second derivative. So y satisfies y double prime plus 2y prime plus y equals 0. Let's find them. So why am I starting with y double prime? That is the silliest thing I may have ever said. You should always start with the first derivative, which is e to the negative x times negative 1. And then the second derivative is going to be negative e to the negative x times negative 1, or positive e to the negative x. if I plug this in, y double prime is e to the negative x. 2 times y is 2 times 2 times y prime is 2 times negative e to the negative x. And y is again e to the negative x. And it looks like I have 2 positives, I have 2 negatives, they add up to 0. That checks out, it's true. Nice and nice. Let f of x equal cosine of 1 over x. Then f of x is differentiable at x equal to 0. Everybody should be able to know the answer to this question just by looking at it. It's definitely going to be false because this isn't even defined at 0. Not only do you have to be defined, you have to be continuous. This function is neither of those things. If you're undefined and or not continuous, you're definitely not differentiable. So not differentiable is false. You make sure you read the question carefully as well, so you make sure you're saying that you might know the right answer. Make sure you're saying the thing that corresponds to that right answer. All right, last question before we go back to this first one. The equation of the line of slope 5 passing the 2, 1 is given by y minus 2 equals 5 times x plus 1. That feels kind of unkind. Now that's false. It should be y minus 1 equals 5 times x minus 2. And unless we were unluckily the same, those should be different. Let's double check. This is y equal to 5x minus 10 plus 1 is minus 9. This is not the same. This is y equal to 5x plus 5 plus 2 is plus 7. No, they're not the same. But he's trying to trick you, right? He's like, oh, let's make it a little bit tricky here. All right, let's look back at this first true false one. So let f equal x times sine of 1 over x for x not equal to 0, and f equal to 0 at x equal to 0. Then f is differentiable at x equal to 0. I think this is true. I think we've done this problem before on the other practice exam. But the way we would show it, or at least check it out, say, okay, well, I think you have to use limit definition here. I don't think you have any other choice. So I'd point out that f prime of 0. I'll check one thing. Oh, you know what? It's false. But I don't want to check the derivative, but I actually am going to check. This is not a good true false question. This is too much work for a true false question. But here's what I know. I know that this function is not continuous at 0. Here's how I know it. What's f of 0 equal to? They tell us in the problem. F of 0 is 0. When x is 0, the function is equal to 0. So for the function to be continuous, which it has to be differentiable, the limit as x approaches 0 better also equals 0. Oh, damn. No, it isn't going to be 0. I'm silly. I was making a classic mistake. Here's a mistake I was making. I was doing the limit as x approaches 0 of x times sine of 1 over x. And I was going to think it was 1. I was going to be wrong because I was going to write it as the limit as x goes to 0 of sine of 1 over x over 1 over x. And that limit, although we have sine of a thing over the same thing, is that thing going to 0? Not. That thing is not going to 0. We can't say that limit's equal to 1. It's not equal to 1. That limit is 0 by the squeeze theorem. So probably is true. Let me get some other paper here because there's not enough room here. So I will point out that if f of x is equal to x sine of 1 over x when x is not 0 and 0 when x is 0, we got to show it's different, or we have to at least justify to ourselves it's differentiable. So f prime of 0 is equal to the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. We definitely did do this problem before on the other practice exam. It's okay to do it again. So I would point out, recognizing that this problem showed up on both practice exams, to me says it's probably likely you might see it tomorrow. So how do we deal with this? Well, f of 0 is 0. F of h, Well, h is specifically not 0. So f of h is h times sine of 1 over h. So we get h times sine of 1 over h all over h. I think this is going to not exist, actually. I thought it was going to be continuous or differentiable. I apologize for being wrong, but I didn't know any better. So canceling the h's. Yeah, canceling the h's. It's disappointing. We have the limit as h approaches 0 of sine of 1 over h. And that limit doesn't exist. Right? As h gets closer and closer to 0, 1 over h just blows up and you get sine going back and forth, back and forth, back and forth, back and forth, back and forth. So I was wrong. I'm pretty sure it's false. Actually, let's double check. Let's see what the solutions say. Maybe I'm wrong all the time here. Stranger things have happened. Let's see here. So looking at the... Yep. Okay. Nope. That's exactly what we just did. Yeah. How unexciting. Oh well, it's boring. Not boring, just I was hoping for a different result. All right. I think we've done enough. Also, I'm not feeling my best, to be perfectly honest. So let's call it a day there. Good luck on your exam tomorrow. I think you have a pretty good idea of what to expect. Study appropriately, sleep well, eat breakfast, give yourself all of the things you need to take your exam well. And probably the best piece of advice I can give you is make sure you read the questions on the exam carefully. That's the number one thing you can do to give yourself the best chance of success. You'll do fine. Good luck. We'll see you all next week. You too.